Welcome to the lecture on heat treatment of castings. So, in this lecture we are going to discuss about the heat treatment of plain carbon and alloy steel castings. So, basically we are going to deal with the steel castings in the ferrous group. So, what is the need of heat treatment? As we know that depending upon the suitability of the composition or properties, or depending upon the ease or depending upon the requirement, different kind of molding processes are selected. It may be sand molding, it may be die casting or any other kind of molding process. When the casting is taken out, not necessarily the casting has the properties what we desire to achieve. So, what happens that during the casting there is large amount of gases which are likely to be inside the casting. There are different section thicknesses of the casting and the properties also vary. So, you may be in a position, you may not be in a position to use this product directly under any application, because if the heating rate is not proper or thermal gradient has been quite high, there is large amount of residual stresses which are likely to be inside the casting. So, casting if it is used and if the impact loads are coming into picture and if the toughness is quite low, in that case the casting may break. So, below that strength where it is expected. So, there are properties which are required to be removed. The structure is needed to be seen, that you get the proper phases, proper structure of the material, because ultimately that only determines what will be the property of the material and how this material will basically behave when it is subjected to the different kinds of loading. So, when the casting is taken out, during that process, since there it is thermally treated, its property changes at many places and there are certain things which are required to be done. Certainly in casting, normally when we talk about the sand casting or so, you have the formation of residual stresses inside the casting because of uneven cooling or because of the presence of thermal gradient. You may also need to go for treatments like in which you may get the good hardness of the surface in certain cases. You may like also to get good toughness of the material. So, all these things are to be incorporated in the casting product. So, that is done by the heat treatment process. Now, there are, so for removing modifying the properties and for stress relieving, that there is need of heat treatment process. Now, as we know that this heat treatment process, in that basically there is transformation going on. The material has certain structure, certain phases are there and they are basically further reformed, they are redistributed. There is formation of one phase at the cost of other, or there is morphological changes in that. So, basically it is all going on and that is a kind of transformation which is going on. So, as we know, this transformation is normally using the nucleation and growth. So, what happens that in the case of ferrous castings, as we see, we can see the iron carbon diagram in these cases. So, you have steels coming up to this range of carbon and then you have, in the case of alloy steels, you have different alloying elements. So, what happens normally your heat treatment is, so when you are talking about the plain carbon steels or so, your reaction which is primarily taking place, that is controlled by this reaction which is taking at this point, this is the eutectoid point. So, at the eutectoid point you have the austenite in this zone and this austenite basically will be decomposing to ferrite plus cementite. So, that is your eutectoid reaction. So, when it is cooling, the austenite will be decomposing to ferrite plus austenite, ferrite plus cementite, and when we are basically heating, in that case this ferrite plus cementite, so that this composition is perlite, so that will go and change to the austenite. So, this transformation at this point as well as the transformation at all these places, maybe below also you have transformations taking place. So, basically this transformation is using the nucleation and growth process, and this nucleation basically is on the impurities at the grain boundaries that is there, on that places the nucleation takes place, and this way you have first the parent phase and then you have the product phase coming out of the parent phase. So, you at the expense of the parent phase new phases are coming up, that is product phases are coming up. So, there will be nucleation of one phase from the other, and this way at the end you have a different kind of structure which gives you different kind of properties, because all the phases have different properties, like you have the ferrite which is extremely soft, but then it is not stable at room temperature, and in this zone you have the cementite, austenite which is FCC. So, you have this has a good deforming properties. So, being FCC you can go in this range and then it has got good plasticity, and then further you have, so in fact cementite if it is more, it is extremely hard and brittle. So, depending upon also the kind of phase, like you have the formation of martensite, that is BCT, that is transformed because of the formation of martensite from austenite because of the rapid cooling that we will discuss later. So, all these formation of different phases will basically determine the quality of the casting as far as its properties are concerned. So, what we see is that you have this point above and below which you have here ferrite plus cementite, that is perlite, and then this is austenite, and how this transformation takes place. So, as we know that you need certain undercooling below which the nucleation takes place, then this after this nucleation there is growth taking place. So, if you take the transformation process, normally there is the transformation is time dependent also. So, you have a time temperature transformation graph that is known as TTT curve. So, if you look at the TTT curve, it is for electrolyte composition of steel. So, what you see is when it comes below this temperature of lower critical temperature, that is AC1 or AE1, in that case once it goes below that temperature the nucleation will start, or transformation basically starts. Now, depending upon the time, you have different kind of phases being transformed. So, above this temperature you have the austenite. Now, once you are coming and with time the temperature is decreasing. Now, if you look at this, you have many ways by which you can basically decrease the temperature inside the melt. Now, what you see here is when you cool in such a manner that now you see this line, one is the transformation start line and another is the transformation finish line. So, if you try to see the curve, basically this curve is nothing but you have, so this way it goes. Now, what you see is it is shown here. Now, this is your equilibrium temperature, and once you are coming, you suppose heat in this fashion, you are cooling in this fashion. Once it touches at this, so this line is transformation start. start of transformation, and this is finish of transformation. So, what happens when you are cooling and the stage is reached, when it touches this line, the austenite will start transforming to another phase. So, austenite will basically be changing to perlite. So, perlite is nothing but the alternate, you have alternate lamellae of ferrite and cementite. Now, and when it comes here, then this is the 100% transformation of austenite to perlite. Now, if you look at this and if you look at in this fashion, what you see is this is having a line indication of higher cooling rate. So, what happens when you have a slow cooling rate going on means this is a time axis. So, for a certain temperature drop you are taking this much of time and you are taking smaller time for this temperature drop. So, what you see is if you take these two lines, the cooling rate experienced or cooling rate given is higher in this line. Now, what you see is depending upon this TTT curve you can predict what kind of structure you are going to get. So, if you are having a very coarse type of perlite, it means the material is basically or casting is subjected to a heat treatment where it is it is cooled very slowly. So, normally in the case of annealing, when we cool in the furnace at a very slow rate, in that case if your transformation is finishing at this point in the upper portions, you see this upper portion where it is finishing, it will be normally giving you a coarse perlitic type of structure. So, this way this is the time temperature transformation curve which tells that how with time and temperature the transformation gives, because transformation product is a function of the nucleation rate and growth rate. Now, in this case if you look at here, if in the case of slow cooling rate, because of the higher temperature it is experiencing for larger time, the nucleation is not predominant, in fact growth becomes predominant, and since nucleation is not predominant, the growth process leads to formation of the coarse kind of structure of the perlite. That is why you get this coarse perlitic structure when your cooling rate is like this. But if your cooling rate is higher than this line, if the temperature difference is more in the same time, in that case you are getting a fine perlitic type of. So, here you have coarse perlite, here you have fine perlitic structure. Now, this is called the nose of the C curve. So, if it is crossing through the nose of the C curve, so this point up to which if it crosses, then there is formation of perlitic structure, and depending upon the cooling rate you have either the formation of coarse perlitic structure or the fine perlitic structure. Now, what happens as we see the next range is the benitic structure. So, in these cases what happen, this is a kind of phase that is benite. So, it has the different kinds. So, here you have cementite in the needle shape. So, because of the larger cooling rate and because of being in the lower range, here this is nothing but the carbide particles are there, but they are in the needle shape embedded in the ferrite matrix. So, that gives better properties in the case of. So, you see in this case you get ferrite plus benite. So, you get upper benite which is feathery type, and this is a scissular type of benite, that is known as lower benitic structure. So, you are getting these benitic structures. Now, what happens when we go? So, for getting this, you have to pass the nose of the C curve. So, once you have the cooling rate which is passing to this line, that is known as critical cooling rate. So, basically you are avoiding the transformation of austenite to perlite, and you have two lines which is shown, one is MS and MF. As it is seen here, you have this MS and MF line. So, MS and MF line talk about martensitic start and martensitic finish lines. So, what you see is when it goes below this temperature, then there will be start of martensitic phase formation. So, if it goes past the nose of the C curve and it passes, so here from downward the martensite will start to form, and this is the martensitic finish process. Now, what happens for getting such benitic structures? Normally what we do is we come here and in this, and basically here if we hold it at that temperature and go in this benitic range, then there is a process known as Austempering process. So, basically you have Austempering process gives you a benitic type of structures. Then there is another process, that is Martempering process, because formation of martensite is basically inducing a large amount of stress, and martensite phase is extremely hard. So, and it induces a large amount of stresses. So, what happens when you come to this point, then you hold for some time. So, you are coming to this point above the MS temperature and holding, and then without going into this range, you are going into this in between the MS and MF line and passing this MF line. So, in that case you are getting completely martensitic structure, but by holding this line at this point for certain time, basically you are allowing the diffusion to take place and having proper homogenization or proper temperature distribution. In that case, the chances of having large amount of stresses, that becomes small. So, this treatment is known as Martempering process. So, by looking at the different kinds of these phases at all these points, and by studying these TTT curves, you can control that what kind of heat treatment should be given, so that a proper or a desirable phase is formed and the casting has that kind of properties what you expect. Now, we should discuss about certain type of processes which involves heating in the austenitic range and then further cooling. So, as we have seen that the TTT curve shows that in what case what kind of phases are being formed. So, the process which are basically based on heating the material in the austenitic range and then further cooling. So, one is normalizing. So, this normalizing is based on the concept that you are heating the material in this temperature. So, this is the A1 line and this is the ACM line, this is normally known as. So, you are heating 50 to 100 degrees centigrade above this A1, this A3 line or ACM line, and then you are cooling in the normal air. So, that basically is known as normalizing. So, normalizing gives you a good combination of tensile strength, ductility. So, that is done for the hypereutectoid or hypoeutectoid steels, where it is heated above this either A3 line or the ACM line, and then further allowing it to cool in the air. Then full annealing. So, full annealing basically you are done for normally for hypoeutectoid steels. So, you are going to above about 100 degree C above the A3 line, and then you are cooling in the furnace at a very slow rate. So, that process is known as full annealing. So, you are holding in the furnace for some time and then you are cooling at a very small rate. So, normally to give very soft property, to impart the toughness, to impart good machinability, you give this full annealing treatment. But in this case there may be chances that the structure may be coarse. So, that is there, but otherwise to make it soft and all the material becoming stress free, this full annealing treatment is given. Isothermal annealing. So, this isothermal annealing, it is done. So, in this case also you are heating above A3 or ACM temperature, and then you are cooling it at a temperature below this critical line and then holding there for a large amount of time at that temperature. So, that is why it is known as isothermal annealing. Then this is homogenization annealing. In homogenization annealing, what is done is the material is heated in this temperature, it comes about 11 to 1200 degree centigrade, it is heated there and it is also held at that temperature for large time. So, this homogenization annealing is done to basically ensure that there is no segregation of alloying elements. Many a times you have segregation of alloying elements. So, this homogenization annealing in which it is going to higher temperature, hold at that temperature and then further cooled in a very slow manner, that basically redistributes these alloying elements, and then it also improves its plastic workability. So, this way after, so when we are going to deform the material plastically in stages, in those cases we do this homogenization annealing in which its deformability or plastic workability increases. So, when we go and give this treatment, then comes hardening. In hardening, again you are heating the component above A3 or ACM line and then you are quenching it into any medium like water, oil or brine solution. So, what happens, this cooling rate is so fast that there is extremely hard surface is achieved, and also depending upon the thickness, section thickness, you will have the formation of hard phases like martensite up to certain depth or the full section being martensitic. That again depends what kind of TTT curve it is, what kind of cooling curve it is in that case. So, depending upon that you will have the formation of phases and you have a hard structure being formed. So, for increasing the hardness you go for this hardening treatment in which you are heating them in the austenitic range above 50 to 100 degree centigrade above A3 or ACM, and then you are quickly quenching it into oil, water or any suitable solution like brine or so. Then after hardening, this tempering treatment is done, because if the martensite is formed, it is extremely brittle. So, to give some softness to it, to make it little tough, you give the tempering treatment where you heat to slightly lower temperature 400 to 500 degree centigrade, maybe the temperature ranges from 200 to even 500 degree centigrade, and then you are keeping at that temperature for some time. So, that basically gives some softness in that phase which is extremely hard, that and that basically makes it somewhat tough. So, this treatment is done to induce the toughness and softness. tempering and austempering. So, we have discussed about it. In the Martempering case, you are austenitizing the material and coming back and holding above the MS temperature, and then after some time again cooling, so that all the phases are martensite. So, this because of the holding for certain time, you have enough time to basically even make the temperature even at all the positions, all the points, and then once you are dipping, once you are cooling in between the MS and MF range, if the temperature is coming, then in that case total martensite structure is formed. So, this way you get the martensite which is not extremely hard and brittle. Austempering already we have discussed, where we are holding and going into the benetic range. So, that is austempering. Then there are also certain treatments or processes which are based on heating in the ferritic range and then further cooling. So, basically we have talked about the austenitic range. So, we are going above the temperature lower critical temperature line, and basically that line is also shifted, or this zone of austenite is also shifted because of the addition of many alloying elements. So, either it may shift towards upside or towards the downside. Now, in this case what you do is the temperature is kept below. So, it is only heated in the ferritic range, and there after you do these treatments like soft annealing. So, you are going below this. So, all these temperature treatments are done soft annealing. So, that is basically to remove, so it make it more tough. This is for removing the stresses. So, normally you are going. So, in this case basically this you are holding this around maybe heating to 500 to 600 degrees centigrade and then keeping at temperature for a long time. So, what happens, these spherical type of carbides are formed. So, that induces so the softness, and you are having good machinability of the material. Similarly, you are stress relieving by heating at about 400 to 500 degrees centigrade and then holding there for some time and slowly cooling. So, that removes all the residual stresses which are there inside the casting. Anti-flaking treatment, this is done to remove the hydrogen which is locked in. Basically, hydrogen if it is there inside, that may lead to stresses and that may cause the cracks, that is known as flakes. So, because of this presence of hydrogen, these flakes are formed. So, you will have to remove this hydrogen. So, for that what you do is you heat and then you have to maintain that temperature for long. Now, one thing is that if your casting uses vacuum or some other treatment, in that case this hydrogen can be removed, but otherwise in this also you are heating and then holding for a larger time, so that the hydrogen which is there, that can go out and it becomes hydrogen free. So, you have different kinds of heat treatments for these steels, and these heat treatment processes induce different kinds of material properties. You might have the treatments like hardness to the skin. So, you have the surface hardening, you have many methods of surface hardening, like you may have the flame hardening, you may have the carburizing, you have nitriding. So, different kinds of surface hardening is also carried out many a times. So, that if you feel that the core should be soft and only surface should be hard, you can go for these surface hardening methods. So, these different kinds of heat treatment methods induce the different kinds of properties which are required for the casting. Thank you.